We are going to start our next session on the future instruments for ELTs. Thank you all. So we'll start off with a talk from Olivier Absil from the University of Liège on METIS. So please take it away.
All right. Thank you. So I'm going to give you a status report on METIS on behalf of a big consortium, obviously. And what I'm going to try to show you today is how we are getting ready for our first high contrast science with the ELT. So is this working? Yes. So METIS is one of the first two instruments that will hit the sky at the ELT, the second one being Mikado, that will be talked about just after me. METIS is a mid-infrared instrument, so it ranges from the L band to the N band, 3 to 13 microns, and it covers a series of different modes, ranging from imaging to long-slit spectroscopy, and finally integral field spectroscopy at a spectral resolution of 100,000. And so I highlight here in blue the modes that also feature high contrast capabilities through chronography. So the imager and the IFS will both feature chronographic capabilities. So in terms of chronographs, the rationale for selecting the chronographic concept was the following. So first we wanted to have the smallest possible inner working angle in order to cope with the long wavelengths at which we are going to be observing. We want to have a high throughput because we know that what we will be fighting for will not only be the specules but also the background, which is pretty high at mid-infrared wavelength. We want the chronograph to be robust because we don't know exactly what we will cope with in terms of ELT performance at the start. And we also want them to be, of course, of high technology readiness level in the mid-infrared. So for that, we selected two main concepts. The first one being a charge 2 vortex chronograph, for which we have a long experience on Sky. And the second one being a grating vector APP, working only in the shorter part of the spectrum of METIS. And so the vortex will provide the smallest inner working angle with the highest throughput, while the APP will provide higher robustness while still having a good small inner working angle. And so you see on the right the different modes showing the fact that the classical vortex will only provide a stellar light extinction by a factor of about 100. And if you want to go deeper than that, you need to add an apodizer, which we also do in METIS. So as I said, these modes can also be combined with our high-resolution spectrograph, which we call the LMS spectrograph. And what you see here is a footprint of the image slicer superimposed on the PSF of the APP and of the classical vortex. And so you see here that the dark hole created by the APP is just about the size of the image slicer, maybe just a little bit smaller, while the vortex will allow us to go on axis as close as possible to the star. This is where we're at right now. So this is a cartoon of our instrument showing that we have a lot of subsystems that are all included into this big cryostat. So there is a command for optics. There is an adaptive optics system, of course, the imager, and the LM spectrograph. And so what you see here is the distribution of chronographic elements inside the instrument, and so you see that they are all over the place. So there is the apodizer here in the first pupil plane. There are the vortex chronograph here in the second focal plane. And then you have the APP produced by Leiden here in both the imager and the LMS, and finally the LEO stops in the pupil planes over there. And so all these guys are now available in our labs. They have been tested. Well, some of the testing is still going on, and they're going to be integrated into the subsystems later this year. And all the subsystems will be integrated together inside the cryostat, and we can start system-level testing in 2028. Until then, what we can do is to do end-to-end simulations to predict what will be the performance of the instrument. And so for that, we use adaptive optics simulations from which we obtain residual phase screens that we propagate through our instrument model in order to produce instantaneous PSFs, on top of which we add the radiometric budget, the background, and in order to produce a mock observation sequence that is hopefully as close as possible to what we will get on Sky. So when we get that, we can pass that through our post-processing algorithms, which are implemented in the VIP Python package in order to get row contrast curves and the post-ADI contrast curves. Just a few words about the effect that we include in these end-to-end simulations. Of course, we have SCAO residuals. There is a poster about SCAO out there. So we introduce other atmospheric effects, in particular atmospheric dispersion and water vapor, which I will talk about in a couple of slides. And CPAs as well has been a major focus for us in the last few years in order to model them and also to find ways to correct for them. We also introduced pupil-related effects, such as the fact that the 798 segments of the ELT will not have the same level of aging, so which means that they will not have exactly the same transmission. There might also be some misaligned segment that might create these kind of little flowers there, where segments will be looking at the dark sky instead of looking at the target of interest. But now, most importantly, NCPAs. In order to simulate NCPAs as best we can, we have used a full end-to-end model of the instrument using Zmax and Proper. And one of the effects that we have been simulating is the effect of chromatic beam wander. So what that means is that when you lock your beam with your K-band adaptive optic system, you will have the L-band beam moving around as the telescope is tracking the star in the sky. And so this will lead to two things. First, the level of atmospheric dispersion will depend on the altitude of the star, but also because you track the pupil, there will be an effect of the dual rotator that will make the beam of the L-band beam move around, creating this kind of slowly varying NCPAs, phase aberrations inside the instrument. And so this we have simulated, and this creates both phase and amplitude aberrations because you have some optics that are not in the pupil plane that also create amplitude aberrations when they are propagated towards the pupil plane. So this is our main source of quasi-static aberrations, or at least we hope so. Otherwise, we have a problem. And the second main source of NCPAs when you operate in the mid-infrared is water vapor. So your AO system working at K-band sees a wavefront that is not the wavefront that the chronographic instrument will see at the L, M, and N band. And this is because of the chromaticity of water vapor. So you have an inhomogeneous amount of water vapor in the atmosphere that is blown by the wind, just like dry air turbulence, except that in this case, there is a big phase difference between what we see at the K-band and what is going to be seen by the instrument at longer wavelength. And this is what is shown here. So we have been using over the last couple of years data from the VLT interferometer in order to constrain the strength of this effect. And now we predict the amount of additional wavefront error that will be seen at the L band and here at the N band. And you see that the additional amount of wavefront error that will be seen by the instrument at N band is much larger than the residual from the adaptive optic systems. So we really need to do something if we want to hit the best performance that we can, especially at N band. And so for that, we are going to be using focal plane wavefront sensing. And so the idea is to use in real time the data from the science camera, which will be running at a fast rate because we are working in the mid-infrared, so typically one frame every 10 to 40 milliseconds. And we will feed that to a neural network that will try to reconstruct the phase in real time as we observe. And so if you want to know more about that, I invite you to look at Gilles' poster out there. I think it's 110, something like that. If you do that, and if you do that in real time, so what we do is to use an asymmetric pupil mask in order to enable instantaneous retrieval. We're not using any kind of sequential phase diversity or phase retrieval. It is an instantaneous process, and in that case, we can reduce our wavefront error from about 200 to 300 nanometers down to 50 to 70 nanometers, which is shown here. And I'm going to play this movie here that shows the PSF of the vortex mode here, the input aberrations from the NCPA, which is mostly water vapor seeing, and you will see so the correction here only for 20 modes at a frequency of 10 hertz, reducing the amount of wavefront error down to this level where we can operate. So this is for N band. operation at L band will go down to about 20 nanometers, which is quite good for this kind of wavelength. On top of this classical integrator that we use here for these simulations, we're also now looking at reinforcement learning, and this is something that Marcus already said a few words about, and there is a poster by Iram Su out there as well. Okay, so when this is all done, we have produced our mock data cube that we can now process in order to predict the performance of the instrument. And this was shown here. So this is our prediction of the L-band contrast curve for METIS. We expect to be around 10 to the minus 5 at 0.1 arcsecond. This is not as spectacular as PCS or J-MAGAO-X, but this is good enough to do good science at the L-band, especially when you compare to what has been achieved on Sky at the L-band with similar instruments on 10-meter class telescopes in the past. Now looking at the N-band, one of our prime targets will be Alpha Centauri, and these are two simulations where on the left I have completely turned off the water vapor seeing, and on the right I make absolutely no correction for water vapor seeing. And I've injected here two planets, Earth-like planets, at first in the habitable zone here, at Earth temperature, and here twice as close. And so you see that if we manage to correct for water vapor seeing, we will be able to see these planets after about 5 hours of ADI observations. To be a bit more quantitative, these are the contrast curves that we hope to see at N-band. So the dashed line are the contrast curves that you get without any correction of water vapor seeing, with different assumptions in terms of the quartiles of the observations here. The gray curve is the adaptive optics performance, and we're going to be somewhere in between, and hopefully just good enough to see these possible Earth twins around Alpha Centauri. Of course, there might not be an Earth twin, especially if you believe the candidate detection of VLT near and MIRI. We might be perturbed by these guys, but of course we will be able to confirm them pretty easily. Okay, so to conclude, this is our timeline. So we are here right now. We have the cryostat already in the integration hall in Leiden, and over the next couple of years, all the subsystems will be delivered to Leiden and integrated into the cryostat. 2028 will be the year where we'll be carrying most of our system-level testing when all the instrument is assembled, which is what we need in order to do the HCI test, until we have preliminary acceptance in Europe and finally shipping to Amazonas. And once again, this is not a simulation. Thank you.
So I may misunderstand things, but if you go from, like, say, median seeing from Amazonas, median water vapor, like 3 millimeters, to the best, like Cerro-Hanar level water vapor, like 0.5 millimeters, how much does the performance change?
Yep. So this is what the color curve are more or less showing. So our first quartile corresponds to about, I would say, 1 to 1.5 millimeters of PWV, which I think will be one of the criteria to schedule any N-band observations with METIS. So we're gonna have this real-time information from the radiometer telling us the amount of water vapor seeing, and we will schedule the observations when the conditions are the best.
I was just going to ask, now that you've kind of figured out how to handle the water vapor seeing, what would you say is going to be the biggest weakness of METIS? And what would you say will be the biggest weakness of this instrument? And if you were given a chance to do an upgrade, even though it's still 4 years away, what would it be?
Well, that's a good question. I think I cannot really answer that until I see some, at least system-level tests, and probably on Sky test, but yeah, I hope that we have identified most of the worst offenders, but yeah, I'm not really sure.
I was wondering how for the N-band, how well is the atmospheric refraction known for correcting and keeping the star behind the chronograph across all of N-band?
Yeah, N-band is not too bad in terms of atmospheric refraction. And actually, for the N-band observations, we won't need an ADC at all. So we have designed the width of the filter so that we are not limited by atmospheric dispersions in our chronographic observations.
Okay, let's thank Olivier again.